All right, so this is Millikan's oil drop experiment. So the question is, what is the charge of this oil? So we can see there's a blob of oil and it's levitating in this uniformly electric field. So basically what that means is that the force of gravity, so that right there is equal to the force electric. So I'll just draw force electric and then force of gravity. They're equal to each other. So the net force is equal to 0 and it's kind of levitating in one spot. So the question is, what is the charge of the oil? So we know the mass of the oil, we know the electric field, and then we also know the gravitational field strength. It's 9.8 newtons a kilogram. So we can use those three things to find the charge of the oil. So let's do that. So we're going to do Newton's second law first. So F net equals mass times acceleration. And there's no acceleration because it's staying in one spot. So this whole thing we can erase and just replace that with 0. And then F net. So there's two things here, right? So there is the electric force and then the force of gravity. So F net is going to equal force electric. And actually, I'm going to make up positive, okay? So up is going to be positive. So force electric minus force of gravity is going to equal 0. And then I'm going to move the force of gravity to the other side. So I'm going to add force of gravity to both sides here. That's force of gravity. So it's going to become force electric equals force of gravity. And then let's expand this out a little more. So this is going to become, so electric field, so E for electric field times Q equals mass times G. And then we're going to arrange for Q. So we're going to move the E to the other side and we're going to get Q equals mass times gravity divided by E. Okay. So I'm going to skip ahead here to show what this looks like when you fill in all the numbers. Okay, so I got my answer here. So 1.44 times 10 to the negative 18. And then another thing we have to note here, so we have to note the charge of this, the charge of it, right? So we have the magnitude, but we don't have whether it's positive or negative. So if we look at this blob here, let's say, for example, if this blob was positive, imagine this blob was positive, which direction would it go in? It would go downwards, right? Towards the negative side. So if it was going downwards, then it would be in the same direction as the force of gravity. So it would just end up accelerating downwards. So that wouldn't be possible, right? So therefore we know that it has to be negative. So if this was negative, then it can have the repulsion force from the negative and the pull force from the positive here. So then it would go upwards, right? So therefore it could cancel out with the force of gravity. So this thing has to be negative. So this is negative 1.44 times 10 to the negative 18. And the second part here is how many spare electrons / protons are there? So the way we can find this is by using the elementary charge. So E is the elementary charge, and that is going to equal about 1.6, actually here, let me write that better, 1.602 times 10 to the negative 19. That is coulombs. So we have to find out how many elementary charges are in this number right here. Because an elementary charge, so proton will have a positive elementary charge of that number, while an electron has a negative charge of that number. So we have to find basically how many electrons are in that charge. So way you're going to do that, so you're going to do number of electrons equals, then you're going to do the same number from before, so negative 1.44 times 10 to the negative 18 coulombs divided by 1.602 times 10 to the negative 19 coulombs. And that should give you a number around 9. So I think it's like 8.99 or something like that. So it's very close to 9. So you can just round it to 9. So number of electrons equals 9. Obviously that's kind of unrealistic in this case, but that would be the number there. So anyways, that is how you do a Millikan's oil drop experiment problem.